So here we are. In this chapter 4, your benefit of understanding what materials are, we're going to take you through a story which will eventually help you understand what some materials are. Some materials shine and some materials are, they conduct electricity. They do a lot of things. They're very hard. And some other materials. And we're going to help you play with them so that you understand them even better. You're going to learn certain things called physical properties, certain things called chemical properties, and also understand what the difference between these things are. And in this process, whatever you see around you might begin to get classified in new ways. You might see so many things around you which you may not have thought about in this way. But from now on, you will be able to see them in a completely new light. You can look at them and say, oh, that looks like a dash. Or this doesn't look like a. And what is this dash? That's what we're going to fill up in this particular chapter. So sit back, because the next few modules are going to be a real trip. And they are best enjoyed when you completely let go of everything else. Set time for yourself. So when you're good and ready to really focus and listen now and relax, play the next module and enjoy learning something new once again. Well. So we're here now, and as you begin to start wondering what's going to happen here, right, you might even begin to feel a little curious, because before you begin to master whatever it is that you think is chemistry, we want you to pay particular attention to how your learning of chemistry begins to deepen, widen, broaden, and become that much more meaningful as you begin to really get curious, jump in, and begin to enjoy learning. Because whether or not you already like chemistry, or you're about to like it in a few moments, the question really is, are you ready for a story? Of course. And how do stories begin? Once upon a time. The moment I say once upon a time, it means that you can sit back, relax, and get ready to jump in and get involved. Because that's how most learning happens, right? Most learning happens when you jump in, feel curious, and begin to go, oh my God, and start asking questions. So it's exactly what we're going to do here. And because the story has begun, you can begin to forget where and who you are, and the world can be free of you for a while. Give it a break. And as you begin to get deeper and deeper into this, the question really is, imagine you're an alien. Right? You're an alien who's somehow suddenly curious about the Earth. You feel really curious about this little planet over there where there's so much hustle and bustle and there's so much activity. So you feel really curious about this little mote of dust on a sunbeam, and then you decide to go check on them. So you're a really advanced alien, you understand. But you have no idea about what happens there. You understand your world. But the moment you go there, you're looking around with alien eyes. You know how it is, right? Imagine looking around this very world with an alien eye. So many things will seem so weird. Like Feynman says, if you were an alien and if you looked around, you will see that somehow a lot of these creatures move around, like things that call themselves humans. And then all of a sudden, somewhere when the light goes down, they all decide to go and put themselves on the bed. They spend 1/3 of their life doing something where they do nothing at all. They go sleep on the bed and stand back up and then come and do something else. It seems very weird if you think about it, right? If you had no idea about this, you'd be very confused. You'd be very confused about people meeting each other, and then each one puts one hand out and they do something like this, and they call it a handshake. And then the same person you meet them again. You don't have to do it. They just walk past as if they don't even know each other. So in one day or in one meeting, they do it only once. If you think about all these little social things that have been set up, which are so obvious to us, when you see them with alien eyes, it all seems very weird. So with these alien eyes, you go. But unfortunately or fortunately, it's not now. It's time to go back in time. So that's why we started the story with once upon a time. So once upon a time, there was an alien who decided to check on Earth. And what he saw, he entered when these probably Neanderthals, so the early men were around, right? And what he saw was a Stone Age. It's called the Stone Age for a reason. So people figured out that, you could we were hunting around most of the times. And then so they figured that if you kill something, if you kill an animal to eat it, right, then you can probably find these sharp stones. They worked really well. They were able to cut things, and they were able to they had to go and find sharp stones, and that was about it. So stones work pretty well. And they knew that they could collect little twigs, and so this guy is watching. So you see this man, as you can see over here. You can see that that person is ready to go and collect some wood, collect some stones. That's all he knows, right? Now what happens all of a sudden is that in all this hustle and bustle of wood and stones, all of a sudden he drops the stone on one particular very innocent looking stone, and clang, there's a noise. Now that's not the kind of noise a stone makes. So he's a little fascinated by that little piece. So he sees that and he goes, okay, that looks a little different. So he takes that little piece that he finds and he thinks it's a rock, it's a very special rock. He sees that, he thinks that because it produces a very clanging noise, he's very curious about it. Then he takes it home and then he tries to break it with other rocks, and every other rock breaks. All the stones are breaking and that one is staying. So it's really hard. And he gets even more curious. He's like, oh my God, I've hit upon something, right? So now this guy begins to start. So as you see this as an alien, so you begin to notice that people are finding these little rocks. And one of them is that they're very hard. And then it's also producing some kind of a clanging noise. He's very confused about it. Now then he starts realizing that if it's so hard, I can break other things with it. So he begins to start breaking other things and he notices something. He notices that as he's doing this, right, the other things are breaking. The one in your hand is not, but its shape is gently changing into something else. Then he realizes that when he takes a really big rock and starts hitting this, it doesn't break, but it starts getting flattened out. Whoa, a rock that can change its shape and still not break. He realizes there's so much potential here. He realizes that, you can start doing crazy things with this. So he starts beating it up into shapes that he wants. And then he notices something even more fascinating. So what he was used to was wood. And then he used to burn wood to keep himself warm. He had figured that out. But then all of a sudden, he takes this weird substance that he somehow created, it somehow found, his lucky stars. And then he began to start putting it on the fire. And what he notices is that it doesn't burn like wood. It doesn't burn like wood, but it does something else that's a lot interesting. So after a while, its color changes. Right? It becomes all reddish. And he's going like, oh my God, what is happening? And all of a sudden, it begins to become water. It becomes liquid. Now today we know it didn't really become water, but imagine him. Right? So as you imagine this with an alien eye, you notice that all of a sudden, there are rocks that hit and they break and things like that. And all of a sudden you've found some pieces that behave particularly differently. So he takes that and he realizes that it's become something like water. It's flowing all of a sudden. A flowing rock? Who would have thought of that? So you see the flowing rock, and after a while, he switches off the fire. After a while, however it had flown, right? It suddenly becomes solid in that shape. So he notices that you can take this weird rock, you can heat it to the point where it becomes like water. And however you make it while it's water, it'll remain there, it'll become solid again. He sees large potential here. He doesn't have to search everywhere to find a solid, sharp rock. All he has to do is take this rock, heat it, and make it into a shape, kind of nudge it into a shape, because now it's become so soft after it's so hot. And then once it dries up again, you get a very, very sharp object. Ooh, what do you begin to observe here? If you've ever played this game called Age of Empires, you will know that our civilization was kind of driven by finding these special substances, right? Initially, we didn't know them. We were in the Stone Age where we were trying to find rocks and then trying to find suitable ones. We're living in caves and trying to do this. But after this, we began to understand these special substances. We began to progress because now you can do so much more. You can start creating shapes that you want to create. You can have harder substances. So when an opponent's trying to hit you and you have a much harder substance, he's going to try and hit you with it and it's just going to break. You have a much bigger advantage. So this substance from our Stone Age to next, if you've played the game, you go to something, eventually you go to the Bronze Age and eventually to the Iron Age. Now these are words that you might be familiar with and they all fall under one big category called metals as we know them today. So the alien begins to get really curious. He's watching all this. He's scrutinizing our civilization with curiosity and he's getting fascinated. Because as he's watching, what he sees is that, oh my God, thousands of years ago, somebody finds some little metal. And from there, it kind of changes the entire path of an entire race and a civilization. Isn't that really interesting? So for an alien, it looks amazing that a substance can change the way an entire civilization works. And the more and more you find these substances, the more it begins to happen. So he begins to understand, and he also sees that the people here have classified, they've understood that, not all rocks behave this way, but many rocks behave this way. So all the rocks that do all of these things that are awesome, they're all called metals. And the ones that don't are kind of boringly called non-metals. Metals feel a lot more special. Yeah, so these non-metals, and there are metals, they keep finding out more and more and more. So all these metals, all the things that we said, right? There's one more as well, right? It's a cold day, and let's say one of these substances, the metals are there. You go sit on that metal. If it's a really cold day, you feel really cold. If it's a really hot day, you feel much hotter than you would on a rock. So something about these makes it so that they respond much more to temperature than a normal rock does. So they're very, very, very special. Now, as the last chunk to your understanding on your way to mastering chemistry is what we're going to do here is name all that you said. So one of the things that he saw was that he wanted to identify these rocks, right? He wanted to identify these particular substances very, very, very clearly, very easily. So he went looking around for them and he wanted to make it easier to see them. And what he noticed was these things called metals had this special property that you could see them and they would shimmer, right? We would now call it luster, metallic luster. So he could find them a lot easier. Amongst normal rocks and these, he noticed that, there is a difference. So it made it a lot easier for him to find them. And then we also know that they are hard. And the fact that he could beat them into sheets, right? Tuck, and you could get the sheets out of them. It's called malleability. How malleable is it? So metals are malleable, most of them. And then he also found that, of course, if you take a 3D structure and beat it down, you get a 2D structure. So you have a 3D block, beat it down, make a sheet. It's called malleability. How much can you do this? It's called malleability. And now, how much can a metal be drawn into a wire? It's called ductility. If you notice, these two are the same, two sides of the same coin. From 3D you go to 2D, it's called malleability. From 2D you go to 1D, it's called ductility. Now, other properties that we discussed about, the clanging noise that actually got his attention towards it in our story is what's called the sonorousness of a metal. And a metal is sonorous. When it's sonorous, it means that when you hit it, it creates a clanging noise, very characteristic. You hit a rock, you don't get that noise. So we've seen a little bit, kind of dipped our feet into this pool of understanding. All we've said till now is what we have seen. What we have not spoken about is why. So my guess is that what we're going to discuss for the next few minutes might be a stretch for a few of you. It's going to be an amazing opportunity for you to stretch yourself and your understanding. Because what we're going to learn now is probably the most basic thing from which everything else stems out. So before you begin to master chemistry and the more complex concepts, the simplest things from which they all flow are going to start over here. Now we saw that there are so many materials and we give them so many names: iron, copper, carbon, lithium, or things that we don't see usually and also things that we see usually, things like copper, like I said. So all these behave differently, right, at the macroscopic level. But like we discussed, to understand how they differ so differently, how they behave so differently, it might be interesting to go at the microscopic level, and that's what we decided to do. Now it turns out that one of the most interesting ways to look at these things is at the atomic level. We know that all objects are made of atoms and basics that we've already learned. And now as you begin to recollect them, you know that the nucleus has protons, has neutrons, and there are electrons that are spread as clouds around it. Now you might imagine them as balls going around, but eventually, very soon, you'll change that picture with little clouds of electrons spread across this little nucleus. Now the interesting thing here is it turns out that these materials are fundamentally classified based on the number of protons that they have in that nucleus. Whoa. You may not know this, but I just stated something that took us years to figure out so trivially. Yeah, the best place to look for is the number of protons, man. That's what defines a particular substance. Whoa, that took us a long time to figure out. So, but standing on the shoulders of these giants that have helped us, and without reinventing the wheel, we know that one of the most fundamental things is the number of protons that are there. So, nice way to go about doing this is to take the simplest one that you can find, right? The element that was formed in the beginning of time, right? The first thing to be formed from the cosmic soup that was there, a simple thing called hydrogen, which was one proton, one electron, right? Just one proton and one cloud in which one electron's there. Great. Now, the fundamental question that must arise is, what is it that's keeping these two together? If these two are individual particles, something must be keeping them together. Now, when you think about that question, we know that on the macro scale, one force dominates, right? It's called gravitation. Now, at the micro scale, it turns out that one force dominates. It's called the electrostatic force. You're very familiar with it. G(mm) by r squared for gravitation, kq1 q2 by r squared for electrostatic force. Brilliant parallel, yeah? And the way they look, right? They're both inverse square laws. Wow, something interesting here. So the more you begin to think about this, you realize at the micro level, you can forget about the gravitational force. Oh, really? Isn't there a gravitational force between these two particles? There is. But the electrostatic force is a million times stronger than the gravitational force. So you can neglect it. Yeah, it's as good as not there. You need not talk about gravitation when you talk at this level, right? So then you begin to think, okay, these two are held together by this electrostatic force. Wonderful. Now it turns out, right, by this really interesting field of study called quantum mechanics that defines that now these protons, which are there inside in the nucleus, are surrounded by electrons, but the electron can't just stay everywhere around. It just can't be roaming around here randomly. There are places where these electrons can be found, and there are places where these can almost with zero probability not be found. So it turns out that way we start getting what are called these shells. Yeah, between two shells, very difficult to find. At those shells, very high probability of finding. So these electrons arrange themselves neatly, and each electron, each shell has like a occupancy rate. It has only a limited number of vacancies. So the first shell happens to have only 2 vacancies. The next one happens to have 8 vacancies, or rather, the next one happens to have 18 vacancies. So on and so forth. So if you have, or rather, the second one has 8 vacancies. If you count 1 and 2, you'll get 10. So you have 2, you have 8, you have 18. You might already begin to see the pattern over here. So what begins to happen now is that once you added 1 electron and 1 proton, you got hydrogen. Now you might think, some of you might be thinking, okay, this is too trivial. Why are we going into this? We're going into this because whether or not you already know this, there is going to be something very interesting when you begin to understand that every single property that you will learn ever in chemistry can be in one sense traced back to this fundamental idea of electrostatic forces between all these particles. So you have a particle, you add 1 more proton and 1 more electron, right? Now what is the number of vacancies in the first shell? 2, right? So this electron can be added to this shell itself. So you have 2 protons, 2 electrons going around over there with 2 things called neutrons that are added to the nucleus. And you might already know why they are there. Yeah. Or rather why we imagine them to be there, because we know that protons together, right? Why would 2 protons stick to each other? They have repulsive forces between them, very large repulsive forces. To hold them together, this you will learn a lot later, there exist forces called nuclear forces that keep all these protons and neutrons all tied up in that nucleus. So we know we are going a little deeper and stretching you out a little bit, and that's for a purpose. So as you're focusing on this, so these neutrons and protons are in the center, and these 2 electrons are going around. Now when we added 1 more electron, why did we also add 1 more proton? Right? That's a question that I would have. I could just add another electron, right? Now it turns out that most things around us happen to be neutral. Now that must also raise another question for you. If the electrostatic force is a million times stronger than the gravitational force, why don't I see it in the large scale at all? 2 neutral atoms here. The protons are going to repel, the electrons are going to repel. This proton and that electron are going to repel, this proton and that electron are going to attract. Yeah, if I said repel there, it's wrong. Yeah. So, but basically you understand that they're all going to cancel each other out. So neutral atoms are much more likely to find. So we are much more likely to find neutral atoms even in our fundamental units. So you take a second element, which is 2 protons and 2 electrons, and then that's called helium. We call it helium. Yeah, that's just like naming someone, right? These names are hardly important. We're looking at 1 proton, 2 protons. And what you observe here is that once you have these 2 protons, now what begins to happen is that now instead of 1 proton attracting this electron, there are 2 protons attracting that electron. Now what does that mean? It means that more force, K, Q1, Q2 by R squared, now the electrostatic force has pretty much doubled, right? If you account a little bit for the other electron repelling, there's going to be some reduction as well. But within the shell, what happens now is that the force is doubled. So the atom becomes a little smaller because more pull becomes, the shell becomes a little smaller. Makes sense till now. Yes. Then the question is, it's going to be very difficult because now closer. It's going to be very hard to knock out an electron from this, right? Yeah. What do I mean by knock out an electron from this? What's going to happen? You put it out in some kind of a temperature situation, many collisions begin to happen. Yeah, this electron is going to be a little difficult to knock out. A lot of energy is required because it's a lot of attractive force. Now, but what becomes really interesting is when you take the next element, as we call it, because it has 3 protons, 3 neutrons, and 3 electrons. Now, these 3 could have been in the same shell, and our analogy would have worked, but by a play of nature and what's called quantum mechanics, from our understanding of it, we know that there cannot exist 1 more electron in the same shell. Now, because we mentioned quantum mechanics doesn't mean this is a complex idea. Understanding why these electrons can't exist in those shells might be complex. But once you accept that, we might pretty much proceed just as pure math. So you have one shell here with 2 electrons and 1 more outside. So this is going to go to the next shell. But now look at this electron. It's fundamentally different, right? You look at that electron outside. It has 1 force on it from the nucleus, pulling it inwards. But another force from these electrons over here, which are going to push it outwards. So net force is going to be significantly lesser because these electrons that are pushing it outwards are a lot closer. And it's k q1 q2 by r squared, right? It's r squared. So nucleus far away, so r squared is going to be large. So the force is going to be lesser, might be lesser than this one. Yeah. But if it is lesser, it would have flown off, it already got pushed off. So we know that it is larger, but definitely it's going to be diminished because of the fact that these electrons are pushing it out. So net force on that electron lesser means what? If somebody comes and collides, yeah, it's a lot easier to knock that off. Yeah, it's a lot easier to knock that off. Now the reason why we're talking about these things is to define or redefine what you probably already know, which is called valency, right? What is this thing called valency? When they spoke to me about valency, they spoke to me as if all the atoms study chemistry at home every single day to make sure that they follow these rules. They told me, lithium, that's the third element we talked about, right, has a valency of 1 because it knows that it wants to, they say statements like it wants to lose that electron. I asked why? Because it didn't make any sense to me. Does lithium know this, right? And when I get analogies like this, I begin to wonder, how exactly does this work at the microscopic level? We might be able to understand it in one particular manner, but doesn't mean anything. So if you look at this, it so happens that they say that complete shells are stable, right? And therefore, lithium wants to be stable. I asked why? And then, so lithium loses that electron and becomes stable. Happy world. I don't understand. I'm really confused. So when I think about this, I begin to think of it this way, right? So if you have this electron, what really appeals to me is, you take it and bring it out. So there's some temperature, right? What is temperature? Merely the kinetic energy, right? So the more the temperature, more things are bouncing around. And so you add it into an atmosphere, right? Some kind of an atmosphere. So you bring lithium in, there could be something else along with it. Yeah, so what begins to happen is that there are many, many collisions happening. And then to me, the probability that the lithium electron that's outside, which is called the valence electron because it's the electron present in the last shell, the outermost shell, it gets knocked off a lot easier because there's some energy available. But the probability that it gets knocked back in is a lot lesser, right? So what happens eventually is that you find that a lot of lithium electrons are knocked out than they are knocked in. Does lithium really want to lose this, therefore it becomes stable? My biggest problem was this definition of stability. I asked, so what is stable? And they said, octets are stable. Now, why are they stable? And the answer was, because they don't change into other things, so they are stable. It made some sense. I'm not saying that's wrong, but to me it just seemed like a beautiful Darwinian story, because if you were to write a book like, Charles Darwin's Theory of Evolution for Dummies, right, and you want to summarize the whole thing in a sentence, and not the important ones, of course, just the things that appeal to people, you would say something like, you ask somebody who doesn't really care too much about Darwin's theory, he'll say, Darwin said survival of the fittest, as if that's what he really said. So survival of the fittest. And if you had gone and asked Darwin, so okay, I want to be fit, I want to survive, I want to be fit. So who's the fittest? And he would have said, whoever survives is the fittest. So fitness is defined by who survives, and the statement, survival of the fittest, is kind of going to make you a little confused. So I know we're going into loops of thought over here. And Darwin's theory is kind of, in that, when stated that way, it seems very, very self-evident or even tautological, right? Who's survival of the fittest? Yeah, the fit survive. Who's the fit? The one who survives. Similarly, I found that over here, yeah, things move towards stability. What is stability? The things that finally end up remaining are the ones that are stable. So the more you begin to think about this, the more you begin to understand that there are two kinds of analogies that we can give. Because many of my teachers were giving me analogies like, imagine you are a philanthropist. You have a lot of money. So they said lithium has extra money. Yeah, that one electron can be equal to extra money. So it wants to give it out. Obviously, because it's a philanthropist. I asked, how do you know lithium's a philanthropist? Yeah, do all people who have extra money give it away? This analogy doesn't make much sense to me. So there are analogies that help you remember, and there are analogies that help you understand and progress the field. Now, I think philanthropist analogy is one of those that help you remember better. Hey, great, no, it makes a lot of sense. Oh, lithium wants to give it away, wants to become stable, and suddenly it gives us the illusion of, oh, I must understand this. But I don't think so. But to me, it appeals a lot more when I think about it as a lot of particles, right? A soup of particles around, everything colliding, and that's what really happens when these things interact. And lithium loses its electron, a very small force enough, because you can see the net force on lithium's electron is very less. And then you begin to start realizing that it's much more likely that at the end of this you find a lithium without that electron than with that electron. Therefore, you call that state of it more stable. And the moment that happens, what's going to happen? Lithium loses electron, what happens? 3 protons, only 2 electrons. Positive charge goes in, huge electrostatic force towards something, goes and attaches itself to something else. So we're trying to do one thing here, which is to explain almost every phenomenon with this understanding of electrostatic forces, because it cannot be any other force, right? Except if you're trying to split the nucleus itself, where it becomes a nuclear force, which is a very, very, very rare case, right? In our entire lifetime, we figure that out like in the past 100 years, somewhere within the past century. So as long as we're not trying to do that, every single interaction that you see must stem from this electrostatic interaction. Now we're going to progress with this understanding that you take one, as you notice this, one proton, one electron, some size, yeah, you can kick it out. Add one more electron, becomes a lot harder to kick it out because they're all really close, much higher electrostatic interaction. So this particular energy that to kick it out that I'm talking about is called the ionization energy. What energy must I supply to this atom to make it an ion? What's an ion? Something that's charged. So a neutral atom is over here. I kick out an electron, it becomes an ion. To do that, I might have to supply some energy, right? You kick out something, you supply some energy. For hydrogen, already decently high because protons and electron are quite close. Then, but as you notice, for helium, it becomes really high like we expect, right? K, Q1, Q2 by R squared, now double the charged particles, much more force. So that much energy I need. But then, lithium, to knock out that one outer electron, the energy drops so low, which again kind of agrees with our understanding of what must happen. Now, what must happen immediately after that, right? It's going to increase a little bit because you're adding one more electron to the same shell. Yeah. Therefore, what are you doing? Increasing the electrostatic forces. So it increases just as we expect. So little kinks in this we can forget, but as you can observe, you take one proton, two proton, three protons, and you start drawing this graph, right? So a graph of number of protons versus the energy required. You get a graph that looks spiky, as you can see, right? Now what this means is that there are high points here, right? What do all those high points mean? It takes a lot of energy to make them lose where they are, and these all happen to be what we call noble gases. One of the first one we discuss is helium, and as you can see there are more. Now we don't want you to go into this too deeply and enjoy yourself too much right now because it's going to come for you in the next couple of chapters, which is called the periodic classification. But the understanding here is that those are defined as stable simply because it requires a lot of energy to oust them from their positions. So when somebody tells me something is stable, my question is at what temperature? Right? Because I can envision some temperatures at which anything becomes unstable. Yeah, you can do anything at all once you start increasing the amount of energy available, in other words, temperature. Because in the sun's core, nuclei are splitting apart. Yeah, talk about helium being stable, right? Not being able to lose an electron. You have enough energy, you can make nuclei come together and collide and fuse together called fusion, and make a nucleus split apart called fission. Right? So stability without telling at what temperature, with what under what energy concentrations talking about, doesn't make much sense. So typically we're talking about normal conditions, and all these seem to be relatively stable in that. So why did we talk about all of this? Is to make you understand that this concept called valency, or the how much is this willing to lose or willing to gain, is not really something that's conscious, but very clearly explainable using electrostatic forces. So if you were chlorine, right, you would have 7 electrons in the outermost shell, and so it's a large amount of electrostatic force between you and an electron. And so an electron comes and lands, you become 8, right? It's much more unlikely that another electron also joins you, right? Why? Because there's a huge amount of electrostatic repulsion from this shell of electrons. It becomes a lot harder. It can't occupy the same shell, it has to occupy the next one. It gets much more likely that it gets knocked out. So after a while you find that chlorine, if you were to take it with 7 electrons, if there is some electron available, it's a lot likely that it takes in that electron because the energy required to do that is a lot lesser than the energy to push it out. So what you find is that chlorine has a valency of 1 because it's willing to accept an electron. Lithium is much more likely to give out an electron. Both of them have valencies of 1. Yeah, or if you want to be more precise, you can call this a valency of -1 if you want to. In that sense, where you're like thinking about whether it accepts it or gains it or throws it away. It's your convention, you can keep it however you want. These are nitty-gritties that we don't have to go into. But the idea here is the more you begin to see these probabilities playing around, right, what's easier to happen? What requires lesser energy? That's what I mean by what's easier to happen, because that keeps changing. As the energy becomes higher and higher and higher, what becomes easy and difficult becomes completely different. So within this temperature, within this energy constraints, what is more likely to happen, what is less likely to happen, and you keep running the show for a while, this whole collision show, whatever is more likely to happen will remain. So when I said it's a stretch for you, it was only because if you really attempt to understand this deeply, you will need this to proceed with our next and next and next and next building blocks, that now that you have the basic set, it's going to be a lot easier to build on top of this.